We are back with perhaps the most important aspect of the controllers in general, of the feedback controllers in particular. We are going to discuss the types of feedback controllers, what we call it as P controller, that is proportional controller, or PI controller, that is proportional integral controller, and we have PID controller, which is called as proportional integral derivative controller. Starting with the proportional controller or the P controller, as you can see in the figure over here, in the equation over here, we have this proportional controller because the error, the deviation which we are able to get, it's simply multiplied by a gain called Kc. This Kc is called the proportional gain of the controller, and what we get is the controller output. Of course, it is also accompanied by cs. Cs is the controller bias, or you can say output of the controller at steady state. Steady state is when everything is well, when there is no change in signal, when there is no error in the signal, and that's the point. With everything is well, this controller has some output, so this output is called cs. So any error over here will be computed in terms of the CT, or you can say that the CS, you can always bring it on to the left hand side, and this will become CT minus CS. This will become CT dash. CT dash in terms of change in the controller output from the steady state, as we had been doing it in terms of deviation variables, putting a dash over here. So this controller output, or the change in controller output, ultimately is proportional to the error. It's simply proportional to the error. That's why the name proportional controller. That's why it's called proportional controller. Now, this Kc can be represented in many different forms. This Kc is gain. This Kc is gain, and this gain can be represented in many different forms. As one form is called proportional band. And how is proportional band related to Kc? It's very simple. Proportional band is equal to 100 upon Kc, or you can say Kc is equal to 100 upon proportional band. Either way. So in case you know the gain, that is Kc, suppose Kc is equal to 20. In that case, proportional band will be equal to 100 upon 20. What is 100 upon 20? It's taken as 5. Or contrary to that, you say that AC is given by 100 upon proportional band. If proportional band is 5, it's normally taken in terms of percentage. Percentage means 5%. Then Kc will be 100 upon 5, that is Kc will be 20. So this is the way the two are related. It's a very simple question that can be asked in normal half mark quiz kind of thing. That proportional band is given, can you calculate the gain, or other way around. So what's the meaning of this 5% or 100%? 5% means that in case the proportional band is 5%, it means that you only need 5% error to bring about 100% change in the controller output. Only 5% change. So output will be 100, input will be 5. In that case, gain will be 20. That's what is justified over here. That's why it's called proportional band. If the proportional band is, let us say gain is 1. If gain is 1 means, in that case, proportional band will be equal to 100%. It means you need to have 100% change in deviation or the error to bring about 100% change in the controller output. That's what the meaning is. So in general, this is the relationship, and normally the proportional band, it normally is observed, it can be as less as 1 and as high as 500. It means that the gain, if you want to compute from here, the gain can be as high as 100 and as low as 100 upon 500, that is 1 upon 5, that is zero point 0.2. So you can see that the gain varies from zero point 0.2 to 100, as high as that. So this is the range in which mostly we going to go in for the proportional controller gains, as we will be tuning it in the future as such. But right now, be very clear, this is the proportional controller equation. Again, as I told you, in terms of deviation, you get like this and you take the Laplace and you get the transfer function of that will be simply Kc. C dash S divided by epsilon S output upon input will be simply Kc. As simple as that. Nothing more. No more discussion on this. We go to the next kind of controller, that is PI controller. This proportional integral controller is very interesting one and perhaps the most popular of all. Let us see how. Coming to the second one, proportional controller, proportional integral controller. We have PI, P for proportional and I for integral. What we see over here, just as in case of proportional controller, we have CT. Just as in case of proportional controller, you have CS. Just as in proportional controller, you have Kc into epsilon T. Nothing so far till this point. But this is the additional term. This is the additional term which we see over here. That is, it is also giving one component is getting added, and that added term is equal to integral of the error from time t is equal to 0, that is when everything was in steady state and you switched over to the auto mode, to the current time t. It's again multiplied by kc as it was here, but you have additional term tau I. This is additional term tau I. I is for integral, tau is time. It's the time constant of integral time constant. It's also called reset time, and normally it is set in minute. Why it is set in minute, you'll get to know in a moment or now. And it's sometimes also referred to as minutes per repeat. It's sometimes called minutes per repeat. Why it is called minutes per repeat, we will get to know very soon. Say if it's 5 minutes, it means that it takes 5 minutes per repeat. What's going to repeat, you will get to know. So this is the term used in as such integral time constant in minutes or in minutes per repeat. The reciprocal of that will be repeats per minute. We will get to that also. But right now, you focus on this term as such. And the value of tau I again can be as low as zero point 0.1 minute. It can be as high as 50 minutes depending upon the requirement. Now, lesser the value of tau I, more is the effect of, because you see it's in the denominator, more is the effect of integration. It takes only zero point 0.1 minute to repeat the effect, or if it is very set at very high numerical value of, let us say, 50, it means it's going to take 50 minutes long time to repeat what, that's going to see. But right now you see that zero point 0.1 is more effective, most effective. 50 is least effective because this tau is in denominator. So higher the value of tau I, lesser will be the effect of integration or the integral aspect of this controller. So, as I told you that some people do not calibrate the controller in terms of tau I, but in terms of reciprocal. Reciprocal, if you take 1 upon tau I, then it will be repeats per minute. Repeat per minute. It's called reset rate. Why it is called repeat? This is what I'm going to tell you again and again. And if you're getting curious, well, good. It's good to be curious. But at this stage, you see that it's called repeat per minute. If 1 upon tau is taken as the overall gains, it's called, sometimes some people call it ki also, but I'm not going to refer to it as ki. I will continue to stick to it as tau I only. And here the entire thing will be very very clear now. We see that if we give a step change, a step error of step, magnitude is, if this is 1 and this epsilon is given a step change, then in that case what will happen, whatsoever is the error, whatsoever is the magnitude, I'm not saying it's unit step, it can be unit step for the sake of understanding, but let's call it as of the magnitude epsilon. Then because of you have two terms over here, you see it was, if you remember, output was equal to kc into epsilon plus it was kc upon tau I, integral of 0 to tau whatsoever, it was kc into epsilon. So that kc into epsilon will immediately at t is equal to 0, this error epsilon has been reduced, and this kc into epsilon will be the immediate jump from here to here. This kc into epsilon is the immediate jump that is going to take place, the change which is going to take place from the initial output of the controller, which was cs at the steady state. So this is the effect of proportional control. This is the effect of proportional control. Now this effect will be repeated. I've been telling you it will be getting repeated. What is going to be repeated? This effect of proportional controller, that is kc into epsilon. It's going to be repeated. After what? How much time you see it's getting repeated? After tau I. Then after another tau I, it's again repeated. After another tau I, it will be again repeated. It will go on moving up and up and up as long as this error epsilon remains. This effect of proportional controller will be repeated every tau I minute. After every tau I minute, we find that the output of the controller has risen by the same amount as was the initial effect of proportional controller. If you have only proportional controller, it will move up and then it will go flat. Nothing more, because it's there. As long as the epsilon is there, proportional will be there. But here, because it's integration, so integral, what's integral of epsilon? It's constant. I've taken epsilon as constant epsilon. So this epsilon will be multiplied by t, and 0 to tau 1, 0 to 2 times tau I, and so on. Tau I is in the time of integration, where we call it as minute per repeat. That's why it's going to take tau minute to repeat the same effect. This will get doubled. The same effect will get tripled. Why? Because the effect is going to be repeated after every tau I minute. That is what the meaning of, you can see once over here again. It's kc upon tau I, and you integrate it. What you will get over here with this tau is, this epsilon is constant. So this constant will also come out, and this dt will become, integral of dt will become t. And in first tau I, from 0 to tau I, this will become 0 to tau I, means tau I minus 0 over here, tau I. So you will get kc upon tau I into epsilon upon this tau I was here. So this tau I and this tau I will get cancelled, and you will be left with kc into epsilon. This was the effect of proportional controller, which is getting repeated after time, every time tau I. If as long as this epsilon persists. This is the beauty of integral controller. The error will persist for longer time, then the output will go on increasing and increasing and increasing till error becomes zero. However small the error may be, output will continue to increase till it is finally able to bring the error back to zero. So this is the beauty of integral controller, and this also becomes the limitation of this integral controller, as you will see in the subsequent slide. So to be, you know, everything comes with a price. We have to see that because of the fact that it continues to increase and increase and increase till the value of epsilon is not brought to zero. So it may become excessively high, and my dear friends, excess of everything is bad. Ati sarvatre vivarjate, something of that sort we keep on reciting in Sanskrit Shalok. So what we see over here is that this aspect, which is the beauty of the integral controller, is the reason we call tau I in terms of minute per repeat, how much time it takes to repeat itself. We say that, I've already given you that this is the beauty, that such a controller can eliminate even the small errors. Smallest error can be repeated, can be eliminated, because it's going to continue and continue and continue to ultimately uh, bring it back to zero. Now coming back to its transfer function, it's very simple. You can see over here you have ct, you have cs, and you can always take the subtraction of the two, and then you can always take the Laplace, and doing this you will get, it's something very simple. You can see the transfer function is given by, because you have integral term, and integral term, whenever you take the Laplace, you have 1 upon s over here, and this 1 upon s is reflected over here. This tau I is the same as this tau I, and this Kc is coming outside the brackets over here. So the transfer function of pi controller as such, which is c dash t upon epsilon t, is given by this equation. It's very simple as such. Now coming to the point where we were saying that excess of everything is bad. Why excess of what kind of excess takes place over here? Suppose I want the level to be 50% and the level actually is 30%. So what should I do? I should increase the flow rate, the inflow should be increased. It's already flowing at the inflow is 80%. I can make it 90%, I can make it 100%. And even if I make it 100%, it's going to take some time for the level to come up. It's not going to come up immediately. And because it's going to take time to go from 30 to 35 to 40 to 45 to 50 and so on and so forth. By the time it reaches over here, the integral will continue to increase the value of output to 100%, to 120%, to 140%. But valve cannot open more than 100%. Valve cannot open to 140%. The signal has become 140% to the wall, but the valve is fully open. There is nothing beyond fully. Now, the issue is that what happens if you just try to catch my words? What happens if the level has reached to its set point, whatsoever it was, and now the level starts moving up? At that moment of time, the wall should start closing. The wall should start to close because it's more than the required level. It has to close from 100% to 98%, 95%. But the signal is already 150%. So it has to come back all the way from 150% to 140% to 130%. By the time it comes to 198, the vessel will be overflowed. This is a serious problem. Output becoming more than 100%, the valve getting saturated. Valve is not going to flow more than open more than 100%. Valve is going to saturate at 100%, but the output of the controller will continue to increase because of the integral action. It has to increase because of the integral action. It cannot stop because as long as the error is not there, it's going to continue to increase. So this kind of thing, when the controller output actually becomes more than what the output can be handled by the physical element, it goes beyond its fully opened position and then continues to pile up to 130, 140, 150 times percent. And it has to come back, instead of coming from 100, it has to come back all the way from 150 to 140 to 130 and 120 and 100. And by the time, things will be out of hand. So this kind of wind up is called integral wind up. This is called integral wind up. And this integral wind up is not something healthy. We have to have some mechanism that by the time we have to put a limit that this integral thing will be there. We honor that, but the moment output becomes 100%, then this integral should stop working. Then this integral should stop increasing the things, so that by the time the error becomes negative, that's in the opposite direction, then it should start decreasing right from 100 and not from 150. So these are the ways we have to see to prevent this integral wind up, to make sure that the output of the controller doesn't become more than 100. The integral should not go on adding its contribution indiscriminately. It has to be tamed. It cannot be left just like that. So this is the problem of integral windup, and that integral windup has to be taken care of by the designer of the controller while it's making its algorithm or its circuitry or whatever. This, my dear friends, I told you that because of the PI controller, the output will continue to change as long as there is a non-zero error. It doesn't become equal to zero. So this error cannot be quickly eliminated. It's going to take time, as I took in case of filling up of the vessel. So because of this thing, the output will continue to increase, keep on increasing, and it is saturated. A valve may be completely open, but it output may continue to increase even after the valve is completely open. And this particular phenomena is called integral wind up. occurring because of the operational changes. You have, certain situations where the error is large and takes a lot of time to change. So the process is to return to automatic operation, and the control action will remain saturated, leading to large overshoot because it has to come back, as I told you, right from 150 back to that. So we need a PI controller which has a special provision to take care of this saturated situation and to cope up with the integral windup. This is what I said is the requirement. This is one of the particular case where in case of PI controller, which is a beautiful controller, which has this property that the integral will continue to increase, is also the limitation, so it has to be taken care of. This is very specific phenomena of integral windup. It's not there with the proportional, it's not there with the derivative, it's here only with the integral kind of controllers. Friends, we're coming to the last of the three, that is PID, proportional, integral, and derivative control. Let's see what's happening over here. We already have seen, just like the previous one, you have CS, just like the previous one. You have Kc into epsilon, you have Kc upon tau I into integral of epsilon with respect to time integral. So this is the new term. This is the new term. Again, it has Kc the way it was, and we have another uh, term called tau d, and this tau d is called the derivative time constant. It's called the derivative time constant because it's multiplied by dE by dt, d epsilon by dt to be specific. So this is the new term, and it means that the output of the controller is proportional to the error. It's also responding to the integral of error for how long the error exists, and it also responds to how fast the error exists. What's the rate of change of error? How fast? Because it's, if the error is small but it's increasing at a very fast rate. Increasing means, oh my god, it's increasing at such a fast rate, so I know that in another 2 minutes it will be too high. I can anticipate, I can predict, I can see what's going to happen in future, I can anticipate. So that's the reason this dE by dt, this term, is going to anticipate the output or the error, and therefore the action of the controller will be high in anticipation what is going to be in future. It's checking the slope of the error, the rate of change of the error. That's why you saw this term is sometimes called anticipatory. It anticipates error, what's going to be in the immediate future. It's also referred to as anticipatory control. I think now it's very simple. You want to play with some mathematics, you can do it very easily. How? Very simple. You take the Laplace. So this Kc will be as such, and Laplace of this will be 1 by s. Kc will be common. So you have 1 upon tau 1 upon s. And since it's a derivative term, so when you take Laplace of a derivative term, then you get this multiplied by s. I think it's a very old story. So this cs goes over here and becomes a deviation variable. So ultimately it's going to be c dash s upon epsilon s. That becomes the transfer function. Of course, because we have taken take care of the deviations, so initial terms, initial condition will be all set to 0, and this is going to be the transfer function of PID controller. Very well defined. We have good amount of anticipatory control, but this anticipatory control, this d epsilon by dt, is not effective every time. Rather, it can be detrimental. Detrimental, not effective. Not effective is very simple. When the error is constant or very small, changing, slow moving, slow moving. Error may be large, error may be long persisting, but its rate of change is very slow, almost zero. So this dE by dt or d epsilon by dt will be zero because it's not going to act for constant errors. Derivative of constant is zero. This is the first limitation of this derivative thing. And the second one is even more drastic. You remember, if you recall, just listen to me very, very carefully. What I'm going to say is that if we have a function sine omega t, and I take derivative of that, it will be omega into cos omega t. If I'm not wrong, omega into cos omega t. This omega comes out in the numerator. And this sine omega t means at what frequency omega it's the error is changing, right? And this error is changing at a very high frequency, at a very high frequency, then the output of this d epsilon by dt will be very very high because it's getting multiplied by omega. If omega is 50, the whole thing will be multiplied by 50. 50 is a big number over here, and if it is 2000, the whole thing will be multiplied by 2000. That's unimaginable. So 2000 frequency, 2000 hertz, noise may be there in the error. The error in the measurement may be there. Error in the environment may be there. It may be getting affected with the transmission lines and so on and so forth. So in any kind of noisy environment, and noise normally is of high frequency, this term d epsilon by dt will be very high, and that very high value of this is going to make the output controller topsy-turvy. So we cannot use this derivative term in noisy environment. It's the second disadvantage. This is of no use when the error is constant. This is the first disadvantage because of this d by dt of something constant is zero. And in the noisy conditions, as we have seen over here, you will have lot of trouble in case we go in for. So in spite of the fact that we are using PID controller, which has all the three elements in it, which has the history, that is the integral, which has the future, that is the d epsilon by dt, which has the present, and that is the proportional controller kc. What right now is epsilon? Integral means what is the history, for how long the error was there, and d epsilon by dt means future, anticipation. So that's how we're going to see we have the present and the past and the future, but then this epsilon d epsilon by dt cannot be used in these two conditions. The two things I have already said, that in case you have d epsilon by dt is equal to 0, you cannot use it, and in case of noisy response you cannot use it because it computes the large derivatives, therefore you have any issues with that. So that's what is about PID controllers. I end up my session till here. In case you have any queries, you can always contact me through the Zoom sessions or through WhatsApp or through telephone calls or through face-to-face interactions, as the case may be. I thank you for being with me, and I wish you a very safe stay. Enjoy learning. Bye bye.